Hi, I'm Pete Knudsen, and I'm here to talk about our SDC project. SDC is our system design capstone. For our system design capstone, our team of 4 is mocking the application Spotify. My part of the Spotify application is displaying all albums that are associated with an artist. For the system design capstone, this video is primarily going to focus on the database selection. So for database choices, I started out, let's just talk about general database selection. I evaluated 7 different databases, selected 2 as my primary choices, where I was going to insert a bunch of records into it and then evaluate them. So for the 7 databases that I started with, I was Cassandra, Elasticsearch, Postgres, Mongo, Couch, and Dynamo. So from that list, I selected 2 primary databases where I would insert records. The 2 databases I inserted were Postgres and Dynamo. For both those databases, I inserted 10 million albums and their related artists into each of those databases. Once I inserted that data, my primary query was, given an artist, tell me all the albums that are associated with it. Both databases, when there was just the raw data inserted with no indexes, primary key, well, I guess it would be primary keys, but just indexes, they were tracking about 3, 4, maybe 5 seconds to return back a query, which in general would not be acceptable. So then I progressed further and put indexes on each of those tables. Once I did that, we got them down to basically 2 to 3 to 4 milliseconds. So pretty much 1,000 time improvement. Let's talk about my database choice. I ended up taking Postgres, and the primary reason was Postgres is a relational database. Mongo is a non-relational document collection database. The primary reason I chose Postgres was because I have very specific relationships. I have an artist, and an artist can be involved in many albums, and an album can have many artists. So I have a many-to-many relationship that I needed to enforce. And if you're going to have a relationship, why would you choose a non-relational database to enforce those relationships? Not that Mongo couldn't do it, but it wasn't quite built exactly for that purpose. One of the challenges I had, and I briefly touched on this, was how do we get from a query taking 5 seconds and bring it down to 3 or 4 milliseconds? Within my Postgres database, in order to speed up that query, I had 3 tables. My artist table, my albums table, and in the middle, my artist albums, which was a join table that would connect the 2 tables in any situation. In order to speed it up, I had to create an index. So I take my artist table and I join it to my artist albums table on an artist ID. Initially, that ID was not indexed. I had to add an index down there. And conversely, from the albums table, I had to add an index on the album ID field. Once I did that, I got it down to about 3 milliseconds. My foreign keys were always enforced, so that it guaranteed that an album had to have an artist that exists, and an artist couldn't be displaying albums that do not exist. Some of the things that I really enjoyed in this project were, number 1, understanding databases, primary keys, foreign keys, indexes, mass loading of 10 million of records. There's some bulk inserts that were really fast. Just to see what happened, I tried inserting data one at a time using regular SQL commands using insert. It's kind of slow, but it was interesting to learn that the process that could be done for both of them. Like I said, my greatest accomplishment, though, was getting both databases to return the data, my query, back in less than 2 or 3 milliseconds, which was more than acceptable time for this project. I look forward to talking at the end of the project where we talk about how fast does that data actually get out to our API and then to the front-end client. Thanks.